Physics students, good afternoon. Mr. Fugit here. In our video today, we're going to be looking at a few problems on your review for test number 5, which covers over the ideas of work, energy, and power. Specifically in our video today, we're going to be looking at problems 3 and 4 on the review. And as always, copies of the review are located on Canvas, as well as a key for the problems that are there. But here we'll be working through them and discussing how to set up and solve problems 3 and 4. So for reference, I will go ahead and read problem 3, and then we will get started. Problem 3 says this: I compress a spring in a dart gun to fire a dart. I compress the spring 5 centimeters and judge the spring to have a spring constant of 300 newtons per meter. How much energy is stored in the spring? So let's go ahead and start there, because this is a few parts. Looks like there are a few parts involved in this question. So we're just going to look at how much energy we store in the spring based on how much we compress the spring and what we estimate the spring constant to be. So, looking for the energy stored in our spring, we have an equation for that: 1/2 K delta X squared, where K is our spring constant and delta X is the change in length of our spring. So 1/2, our constant, is 300 newtons per meter, and we're told the change in length of our spring is 5 centimeters. We'll need to convert that to meters, so dividing by 100 should give us a value of 0.05 meters, and then that quantity is squared. Let's plug this value in and see what we get. 0.5 multiplied by 300 multiplied by 0.05 squared. It looks like we get a value of about 0.375 joules of energy stored in our spring. There's our starting point. Now from there, it says, if I fire the gun horizontally, what is the initial velocity of a 15-gram dart as it leaves the spring launcher? So let's say we've got something roughly like this, some type of spring that's being compressed, right? We're pushing the dart in, and then all of a sudden, and here's our dart that's going to get fired, if you will. Initially, we can assume that this is relatively on the ground. It's not moving, so no gravitational potential, no kinetic energy. All the energy here is stored in our spring, and we found how much energy that was, 0.375 joules. Now we're told then we release the spring, and the dart gets fired, and we want to know how fast it's moving as it's getting fired. Now in this scenario, we're not told anything about air resistance or friction, so we can probably assume that our energy is going to be conserved. The energy we start with, 0.375 joules, is equal to the energy we end with, 0.375 joules. Now, if we're firing the dart horizontally, we can assume that as we fire the dart, our object isn't going to gain any gravitational potential energy because it's not moving upward or downward. However, the dart will have some kinetic energy. It's going from a point of not moving to moving, so it's going to be gaining some kinetic energy. Now, once all of the spring has been released, right, it's returned back to its original position, we can assume there's no more energy stored in the spring. So all of this energy, 0.375 joules, will be kinetic energy. It won't be split between multiple forms, it will all be kinetic energy. So now we use our equation for kinetic energy to find our velocity. 0.375 joules is equal to 1/2 mv squared, where m is the mass of our dart, which was 15 grams. We'll need to go ahead and convert that to kilograms so that we're in standard units here. 0.015 multiplied by v squared, 0.375 joules on the left-hand side. 1/2 multiplied by 0.015 gives us 0.0075, so we've got 0.375 joules still over here on the left. 0.0075 v squared. So now to get our velocity term by itself, which is what we want, we'll need to divide by our value here, 0.0075, and then we will need to take a square root. So those values will cancel out. I'll take 0.375 divided by 0.0075. That's going to give me a value of approximately 50. Remember, that's equivalent to v squared. So now we'll take a square root to get v by itself. Should be somewhere a little above 7. Yeah, about 7.07. And our standard units for velocity here, meters per second. check our key. Good, and it looks like a 7.07 is what we're looking for. So here, it's just a pretty straightforward scenario involving energy conservation. We do make the assumption that we have no friction, no air resistance, so we can assume the energy is conserved. There aren't any forces doing work to take energy away. We assume that we are on the ground, or at least in a position such that our height does not change. So even if we have some gravitational potential energy here, we have the same amount here. So we don't really have to focus too much on gravitational potential energy if we're just looking at something that moves horizontally, at least in this context. And so we look at the energy we start with, which is all energy stored in the spring, set that equal to the energy we end with, which is going to be kinetic energy, and then work algebraically to find our velocity. So again, hopefully this kind of reminds us of what to do in a scenario like this, where we're looking at energy conservation. And we'll now move on to question number 4. And question 4 says this. A car with a mass of 1,500 kilograms, traveling at 18 meters per second, crashes into a brick wall and crumples a distance of 0.5 meters. Using the relationships of work and energy, determine if this crumple zone is safe, under 25 Gs. If not, what needs to happen to the crumple zone to make this car safe? So here, in question number 4, we're actually looking at something pretty similar as to what we did in group problem 6b. So if you want a more lengthy explanation or kind of a more step-by-step process, feel free to reference the video for group problem 6b. But here, this will be problem number 4 on our review for test 5. So here, we want to find, is the crumple zone safe, meaning what's the g-force? So to find g-force, I need the acceleration of our car as it's hitting the wall and slowing down, divided by gravitational acceleration. Now, based on what we know here, we do know some things about masses, velocities. We could maybe use a kinematic equation here. That would be one approach, saying that our initial velocity is 18 meters per second. We could then use that with the delta x, the crumple zone of about 0.5 meters. We could maybe use a kinematic equation here, but let's say we aren't going to do that. As the question states, we want to use the relationships of work and energy. So if I want to find an acceleration, I might need to use Newton's second law, which relates this idea of forces to masses and accelerations. I know the mass involved here, so as long as I can find a force, I know the mass, I can use that to find an acceleration. So how do we find a force involved? Well, forces are part of our work equation, right? Remember, the work done on an object is equal to the force applied on that object, multiplied by the displacement of that object, multiplied by cosine of the angle between the force and the displacement. We also know that work done is equal to a change in energy. So there might be a lot of steps we have to go through if we want to use work and energy to solve this problem. So I'm actually going to start over here by looking at a change in energy, because the problem tells us that our car is moving, it hits a wall and comes to a stop, which sounds to me like we have a change in kinetic energy here. So I would first look at work done as the change in energy, which is energy final minus energy initial. Now, if we're on level ground here, which we can safely assume that we are, we can ignore gravitational potential energy. We're also not told anything about springs. So the energy that we're going to focus on here is going to be really kinetic energy, 1/2 mv squared. Now I'm going to go ahead and assume that our final energy will be 0 because we're hitting the wall and coming to a stop, which means if our velocity term is 0, the value for kinetic energy would be 0. However, I am going to go ahead and find what's the kinetic energy that our car starts with before it hits the wall. That kinetic energy initially would be 1/2 multiplied by our mass, which here is 1,500 kilograms, multiplied by my velocity term, which is going to be squared, 18 meters per second, squared. So we'll take a moment and go and find what that value is. 1/2 multiplied by 1,500 multiplied by 18 squared. Looks like about 24,300 is my initial kinetic energy. Now, that's the energy I start with, and I end with nothing. That means, well, the work done here should be negative because our object is losing energy. So, to bring our equation down here, work done is equal to a change in energy, which is our energy final, 0 joules, minus our energy initial, 24,300 joules. So the work done here is negative 24,300 300 joules. Okay? Negative because our object is losing energy. So now that we have the work done, right, we can actually use this second approach to find the force involved based on the work done and the displacement of the object. So let's use that second approach. We know now that the work done is equal to the force applied on our car multiplied by the displacement of the car. This is all put in context for our problem. Multiplied by cosine of the angle between the force and the displacement. So plug in what we know. We know the work done is negative 24,300 joules, taking away all the energy of the car. We want to know the force involved here. We do know the delta x here. That's the distance of the crumple zone, how much the car crumbles into the wall. That would be 0.5 meters. And we can assume that since the car is, let's say, moving to the right as it goes into the wall, this is our wall over here, well, the force from the wall onto the car is going to be applied in the opposite direction. So delta x is to the right, the force is to the left, so the angle between those would then be 180 degrees. So cosine of 180, which we know is going to give us a value of negative 1, right? Now that negative 1 and the negative 24,300, those will kind of take care of each other there. I could technically divide by negative 1 on both sides. So if I divide by negative 1, that will get rid of the negative on both sides of the equation here. And now to get a force by itself, I'll simply divide by our delta x, 0.5 meters. So 24,300 divided by 0.5, we get a force of about 48,600. Ooh, you know, I'm realizing I left a value off here. So for our kinetic energy, I noticed that I had a little bit of an issue with a value here. The initial kinetic energy, I read this wrong, is not 24,300, it's 243,000 joules, which means our work done should be negative. My apologies for that issue. Yeah, very easy to make a mistake as you're working with some of these equations. So, yes, be negative 243,000. So this value here should be actually 243,000 joules divided by 0.5. That's going to give us 486,000 as our value for the force from the wall onto the car. My apologies, right? Very easy to make a little mistake just reading some of the values from the calculator. So now we have an idea of the force involved between the wall and the car. Now, as we've talked about, that force we can use along with Newton's second law to find the acceleration of the car under these conditions. So now, assuming that the force from the wall onto the car is really the only force in the x direction, we're not told that our car is speeding up, we're not told that it's hitting its brakes and sliding, so we can assume that the sum of forces on our car is really equivalent to the 486,000 value that we just found. Mass times acceleration, we're looking at the x direction here. So 486,000 newtons is equal to our mass, 1,500 kilograms, multiplied by our acceleration horizontally. So now to get the acceleration by itself, we'll divide by 1,500 kilograms to get the variable that we want alone. So 486,000 divided by 1,500. We get about 324. So our acceleration horizontally is going to be 324 meters per second squared. Now that seems like a very, very high value, especially for a car. But remember, this value is not because of how the car is designed to work. This value is so high because the car is smashing into the wall, meaning it changes its velocity very, very suddenly. So now that we have an acceleration, the last thing we can do is find our g-force. So the g-force involved here is going to be our acceleration divided by gravitational acceleration. We've got a value of 324 meters per second squared, divided by gravitational acceleration for the Earth, 9.81 meters per second squared. So we'll divide by 9.81, we get about 33 g's, which means our acceleration is roughly 33 times larger than acceleration due to gravity. Now, according to what the problem statement tells us, we want something that should have a g-force of under 25 g's. This is clearly over 25 g's. So, in order to maybe fix this problem or come up with a better solution, one good approach would be to lengthen the crumple zone so that the force that's applied has a little bit more space to do its work, which would hopefully lower our acceleration and then lower our g-force. Now, as I mentioned for problem number 4, there is another separate video for group problem 6b, so if you want some more practice and resources, that is available for you. As always, keys for these problems are accessible on Canvas. If you have any questions, you're welcome to direct them my way. Good luck.